Hello everyone, this is another video on atomic and molecular physics gate PYQs. We'll be solving the PYQs, gate PYQs of atomic and molecular physics. Alright, I hope you watched the previous video where we discussed 10 questions about in the previous few questions. And in that video, I gave you a homework also. Okay, so it was question number 11. The homework question was the excitation. I will write it again. The excitation wavelength of laser acceleration wavelength of laser in a Raman effect experiment. In a Raman effect experiment is 546 nanometer if the Stokes line is observed Stokes line is observed at 552 nanometer. Okay, then the wave number of the anti-Stokes line, wave number of the anti-Stokes line, okay, is in centimeter inverse is the excitation wavelength of laser in a Raman effect experiment is 546 nanometer. If the Stokes line is observed at 552 nanometer, then the wave number of the anti-Stokes line in centimeter inverse is. So if you see here, we know Raman displacement is Raman displacement. What is it? Del nu bar is equal to nu bar anti-Stokes minus nu bar. Okay, is equal to Stokes. Sorry. Okay, so we can also write when lambda anti-Stokes minus when lambda naught is equal to when lambda naught by minus 1 by lambda Stokes. Yeah, yeah. So if I write it again, lambda anti-Stokes is equal to 1 by lambda naught plus 1 by lambda naught minus 1 by lambda Stokes. So 1 by lambda anti-Stokes is equal to 2 by lambda naught minus 1 by lambda s. So if I take the LCM, it is lambda naught lambda s, 2 lambda s minus lambda naught. Okay, the lambda anti-Stokes is equal to lambda naught lambda Stokes divided by 2 lambda Stokes minus lambda naught. Is that alright? Okay. So the values that are given in the question are what? Lambda naught, that is excitation wavelength. This is the excitation wavelength. Excitation wavelength is given as 546 nanometer. Now lambda anti-Stokes is also given. Lambda Stokes is given. Lambda Stokes is given 552 nanometer. So we'll just put it here. We'll see. Lambda, so lambda anti-Stokes is equal to 546 into 552 all divided 2 into 552 minus 546. That will be the answer. So you will get something here. Whatever you get, if we just take the reciprocal, that will be our wave number of anti-Stokes. So 1 by lambda ax is equal to wave number of anti-Stokes, right? Hmm. So if if you calculate this, you will get something, and you will reciprocate this, and the value that will come is 540.129 into 10 to the power minus 7 centimeter inverse. Okay. Okay, sorry. No, this is your lambda as actually. So 1 by lambda as will be this much. So which is equal to 18514 centimeter. You can use calculator for this. No problem. Okay. So this is how you solve this question. Because see, this is your excitation line at the middle. To the right there is anti-Stokes, and to the left there is Stokes. The difference between them is 6b, 6b, but after that this is 4b and this is 4b. Okay. Okay. Next question number 12. Number 12. Match the phrases. This is a like memorization type question. Match the phrases in group I and group double I and identify the correct option. Identify the correct option. Yeah. So group 1, group 2. Hmm. So in the group 1 there is electron spin resonance, ESR, then nuclear magnetic resonance, nuclear magnetic resonance, NMR, then transition between vibrational states of a molecule, transition between vibrational states of a molecule. S is electronic transition. Electronic transition. Yeah. In the right side there is radio frequency, radio frequency, visible range frequency, visual range frequency. Option 3 is microwave frequency, microwave frequency. Option 4 is far infrared range. Yeah, alright. So the options are, the option A is PI, U double I, R triple I, SIV. Option B, P double I, QI, RIV, S triple I. Option C, P triple I, QIV, RI, S double I. Option D, P triple I, QI, RIV, S double I. Okay, this is a question. Take your time and try to solve this. Take your time and try to solve it. Okay. So could you solve it? See, it's mainly a memorization type question. If you had studied it, only you can answer. Okay. So first is your electron. Electron spin resonance is actually ESR is achieved by is achieved by microwave frequency. Okay, microwave frequency. This is your three. Okay, next is nuclear magnetic resonance. Nuclear magnetic resonance is achieved by what? Nuclear magnetic resonance is actually achieved by a radio frequency. Okay, remember this, a radio frequency. All right, this was your option I. Electron ESR is microwave, nuclear is radio. Then your electron transition is achieved by visible radiation. Okay, visible radiation, which is your option of light. And sorry, this was your yes. My bad. Yes, R is, I missed R. Transition between vibrational states. Transition between vibrational states of a molecule is achieved by what? Radiation of far infrared range. Radiation of far infrared range. Far IR range. Yeah, that's what it is. Electron is microwave. Electron spin. ESR is microwave. NMR is radio wave. Electron transition is visible range. Transition to vibration is far IR range. You can write it here also. ESR microwave. Okay, and NMR is your radio wave. Uh, then electron transition. Electron transition is visible range and like transition between vibrational states, that is far infrared range. Yeah, far infrared. So these are the answers. You can match it and an option also. All right. Okay. So question number 13. Question number 13. Write down the molecule of 17 is what? Raman active, but not NMR active. Iron active and Raman active, but not NMR active. But not NMR active. You see, Raman active and NMR active. Okay. Option D is only NMR active. Only NMR active. Yeah. So these are the options. Huh? So Raman active but not NMR active, IR active and Raman active but not NMR active. Raman active and Raman only NMR active. So these are the options. See, oxygen is answer. Your oxygen molecule is actually what? It can't absorb, it cannot absorb infrared as there is no change in dipole moment. Okay, as there is no change in dipole moment during vibration. During vibration. Thus, 1702 is infrared inactive. Okay, this is one. Okay, another point again we can write this first point. Just write down these points. It may be helpful for you. As oxygen shows change in polarizability, change in polarizability during rotation, right? During rotation. Thus, it is what? Raman active. If there is change in polarizability, it is Raman active. Yeah. Option 3, no, not option 3, like the point 3 is oxygen is has spin, if you see has spin 5 by 2, okay, so it is NMR active. Okay, now you can see which options are correct. Raman and NMR active options. Okay, there is change in polarizability, that's why it's Raman active. It has spin 5 by 2, that's why it's NMR active. Okay, so oxygen is what? Both Raman active and NMR active. Okay, question number 14. In a rigid rotator of mass m, if the energy if the energy of the first excited state the energy of the first excited state is 1 millielectron volt, then then the fourth excited state energy then the fourth excited state energy is what? Okay, in millielectron volt, right? So E, we know what E is proportional to J only to J plus 1, isn't it? Where J is your 0, 1, 2, 3. So E4 by E1 will be what? Because fourth excited state. So 4 into 4 plus 1 by, yeah, first excited state, 1 into 1 plus 1. Alright, so that will be your 20 by 2. Yeah, is equal to 10. So E4 by E1 is 10. So E4 is what? 10 E1, isn't it? 10 E1. That is 10 into 1 ME. That is 10. Okay, see how easy it is, this one. Too easy. Just have to remember this E is proportional to J whole into J plus 1. Then you can solve this question very easily. Okay. Next question right now. Similar type we just did. So 15. No, this is let's do a different one. The term J1, J2 arising from arising from 2s1 3d1 electronic transition electron transition in JJ coupling in JJ coupling scheme R. JJ coupling scheme R. Okay. Options are 1 by 2, 3 by 2, 2 is to 1, and 1 by 2, 5 by 2, 3 is to 2, then 1 by 2, 1 by 2, 1 0, and 1 by 2, 3 by 2, 2 1. Option C. Option C, 1 by 2, 1 by 2, 1 0, and 1 by 2, 5 by 2, 3 2. Option D, 3 by 2, 1 by 2, 3 by 2, 1 by 2, 2 1, and 1 by 2, 5 by 2, 3 2. Yeah, these are the options. JJ coupling from 2s1 and 3d1. Okay, see. 2s1 and 3d1. So S1, that means there is okay. So this is your L is equal to 0 and S is equal to half. Here L is equal to 2, S is equal to JJ coupling. That means this is your J1 values are half only. So J2 will be here. What is the value? 3 by 2, 5 by 2. So we'll just do this with this and this with this, isn't it? So half 3 by 2 and half 5 by 2. And from half 3 by 2 we will get what? Half plus 3 by 2 to half minus 3 by 2. So that is 2, 1. Yeah, I think 2, 1 only. And from this we will get half plus 5 by 2, that is 3. Half minus 5 by 2, that is 2. So this is the answer. Half 3 by 2, 2, 1. And half 5 by 2, 3, 2. Yeah, option D will be the correct answer. Now what? Half 3 by 2, no, 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 no. Half 3 by 2, 2, 1. Half 5 by 2, 3. Correct order is there. This is not the correct order. Option A is the correct answer. Okay. Next question write down. It was your question number 15 or question number 16. I don't know. Question number 16. Question number 16. Given that the ground state energy, given that the ground state energy of the hydrogen atom, ground state energy of the hydrogen atom is minus 13.6 electron volt. Okay, the ground state energy of positronium atom is positronium positronium atom, which is a bound state of bound state of electron and positron. Electron and positron is options are option is plus 6.8 electron volt, option B minus 6.8 electron volt, option C minus 13.6 electron volt, and option D is minus 27.2 electron volt. Okay. Given that the ground state energy of hydrogen atom is minus 13.6 electron volt, ground state energy positronium. So this type of questions come a lot in exam about positronium and hydrogen relations. So just see, easy question, nothing much here. Okay. So energy expression of positronium will be what? Energy for positronium. Energy expression for positronium will be what will be the energy? AN will be for positronium. Suppose P minus 13.6. Okay. uh, 2 n square even, okay, because hydrogen is minus 13.6 n square, okay, for hydrogen. So positonium, it will be energy of hydrogen by 2. Okay, all right, energy of hydrogen by 2. So here ground state energy is asked, right? Ground state energy, so n is equal to 1. Ground state is n is equal to 1, so just put it. Energy of positonium will be minus 13.6 by 2. That will be what? Minus 6.8 electron volt. Okay. Simple. Very simple question. Right? Okay. Yeah. Next question is another question that comes very repetitively in exams. This is a question number 16. No? Question number 17. In the hyperfine interaction, in the hyperfine in the hyperfine interaction in an atom, if the hyperfine interaction in an atom is is given by H is equal to A S of electron dot S of proton, hmm, where Se and Sp the spin of denote the spin of electron and protons respectively. Electrons and protons respectively respectively. Okay. The splitting between the splitting between splitting between 3s1 and 1s0 state is 3s1 and 1s0 state is, okay. Options are A h cut square by root 2. Option B, A h cut square. Option C, A h cut square by 2. Option D is 2 ah cut square. This is the question. Again, read the question twice, and then only you start proceeding with the question. If the hyperfine interaction in an atom is given by H is equal to A spin of electron and the spin of proton, the splitting between 3s1 and 1s0 is how much? Okay, so this is the question. How to approach it? How to approach this question? We know the total spin is what? Se plus sp. Okay, similar type of question, nothing else. We have done it so many times. AC square plus sp square plus 2ac dot ac sp. Isn't that right? 2ac dot sp. So s square minus ac square minus sp square is equal to 2se dot sp. So se dot sp is equal to half s square minus ac square minus sp square. Is that right? Hmm? Is that right? So now if you see, um, now see Se is what? Half. Spin of electron is half, spin of proton is half. So Se square I can write as, what is Se square? I can write Se square as Se whole into Se plus 1 h cut square. That will be what? Half whole into half plus 1 h cut square. That is half into 3 by 2 h cut square. That is 3 by 4 h cut square. This is also for the case of sp square, right? Sp is also same now. So we can just put it here. Half s square minus 3 by 4 h cut square minus 3 by 4 h cut square. Is that alright? Yeah. Why I didn't put the value of s? Because s is different for these two states. So this state s is, see, 3s1. That means this one is your actually 2s plus 1 is equal to 3. Na? So s is different for these two cases. So let's do that. So 3s1. So 2s plus 1 is 3. This is your 2s plus 1 value. So 2s is equal to 2, s is equal to 1. Okay, s is equal to 1. So for this value will become what? Let's see. So for this value will become ac dot sp is equal to half. Uh, yeah, s square means what? S all into s plus 1 minus 3 by 4 minus 3 by 4. 3 by 2 h cut square is equal to half 1 into 2, that is 2 minus 3 by 2 h cut square. Okay, so half 4 minus 3, that is half 4 minus 3 is 1 by 4. Sorry, 4 minus 3 by 2 h cut square, that is 1 by 2, 1 by 4 h cut square. Okay, so this is your SC dot SP for what? For 3s1. Now for 1s0, the other one is 1s0. 1s0, 2s plus 1 value is 1. So s is equal to actually 0 here, right? S is 0. So for that, SC dot SP value will be, for 1s0 is equal to half s whole into s plus 1 minus 3 by 2 h cut square. Yeah, the h cut square should also be there. Yeah, so half, this is 0, this is completely 0 na? 0 minus 3 by 2 h cut square. So that gives me half into minus 3 by 2 h cut square, that is minus 3 by 4 h cut square. Okay, one value is 1 by 4, another is your 3 by 4. So how to get the splitting? The splitting, if we subtract both of them, we'll get the splitting. So splitting del H is equal to, like, AC dot SP for 3s, like 3s1 minus FE AC dot SP for 1s0. Okay, so that is 1 by 4 h cut square minus of minus 3 by 4 h cut square. Okay, so that is 1 plus 3 by 4 h cut square, that is h cut square. Is that all right? Is that all right? And if you see, um, okay, okay, there is another thing here in the question. H was what? A into this much. So no problem. We got this as h cut square. So the whole answer will be A into h cut square. Got it? Clear? This will be the answer. Again, a very good question. This question comes very repetitively in the exam. Okay, so don't worry. You can easily do it. Just you have to use the concepts very well. Okay, next question. So question number 17. Now question number 18. Question number 18. Question number 18 will be ratio of intensities. The ratio of intensities. The ratio of intensities of the D1 and D2 lines of the D1 and D2 lines of sodium at high temperature. Sodium at high temperature is the ratio of intensities of the D1 and D2 lines of sodium at high temperature is option A 1 is to 1, option B 2 is to 3, option C 1 is to 3, option D 1 is to 2. Yeah. The ratio of intensity of the D1 and D2 lines of sodium at high temperature is, so try this question. So, ratio of intensity of D1 and D2 line of sodium at high temperature is. Okay, ratio is what? Hmm? First of all, tell me D1 and D2 line of sodium means what? So, D1 line of sodium is 2p half to 2s half. That is your D1 line. D2 line of sodium is what? 2p 3 by 2 to 2p 3 by 2 to 2s half. That is your D2 line of sodium. Hmm. Sodium lines. Yeah, you have to remember this. Hmm. So intensity, ratio of intensity. So intensity of D2 divided by intensity of D1. That is what we are asked. So we know the formula 2J2 plus 1, 2J plus 1. Okay, so I is proportional to 2J plus 1. Yeah. So 2J2. What is J2 here? In D2. D2, what is J2? 3 by 2. Right. And D1 is half 1 by 2. So 2 into 3 by 2 plus 1. Like what is the j value? The beginning value, okay, from which the transition is happening. That is the j we will take. 2 into half plus 1. Okay, so this is your 3 plus 1 divided by 1 plus 1. That is 4 by 2. That is 2. So the intensity ratio is 2. Alright, that is the answer. It's very easy. 2 is to 1. Sorry, 2. I got 2. Okay. Yeah, yeah, wait. I took D2 by D1. You can take D1 by D2 for your safety. 1 is to 2. Yeah, this should be the answer. Okay, next question. Question number 19. Question number 19. The first absorption spectrum, the first absorption spectrum of 12 carbon, 16 oxygen is is at is at 3.842 centimeter inverse. Okay, while that of while that of 13 carbon, 16 O is at 3.73 637 centimeters. The ratio of their moment of inertia the ratio of the moment of inertia is, okay, let's calculate. First absorption spectrum of 12 carbon 16 O is at 3.842 centimeter inverse, while that of carbon 1316 O is at 3.673 centimeter inverse. Okay, the ratio of the moment of inertia. Yeah. Okay. First absorption spectrum of carbon 12 oxygen 16. So first absorption spectrum is taken as 2b1. Okay, 2b1. Yeah. So b1 is how much? If we right now for 13 carbon 16 oxygen, so 2b2. Okay, that will be 3.673. That will be b2 will be 1.8315, right? Centimeters. So what is asked? The ratio of the moment of inertia. Yeah, moment of inertia. So see, we know B is equal to h by 8 pi square IC. So B1 by B2 will be I2 by I1, isn't it? Because B is inversely proportional to I h by IC. So that implies B1 by B2, that is 1.921 by 1.8315 is equal to I2 by I1. That's it. Hmm. Um, so that will give me I2 by I1 is equal to, if I divide this, we will get 1.046. That will become this one. Okay. Yeah. Okay. Next, a good question right now. Consider the energy level diagram. Energy level diagram shown below. Shown below, which corresponds to corresponds which corresponds to the molecular which corresponds to the molecular nitrogen laser molecular nitrogen laser. Okay, so this is a state like this is a state like this is a transition here, tau to 1, and this is here tau 1, this is 1, this is 0, this is 2, and this is your r. Yeah, so if the pump rate if the pump rate R is 10 to the power 20 atoms, okay, centimeter minus 3 second inverse, and the decay and the decay roots are as shown in the figure, okay. um, and then tau to 1 decay, sorry, decay ratios are, decay ratios are, what are the decay ratios? Tau to 1 is equal to 20 nanoseconds, tau 1 is equal to 1 microsecond. The population of states states 2 and 1 states 2 and 1 are respectively, yeah, respectively, option A 10 to the power 14 centimeter minus cube, and 2 into 12 centimeter minus 3, V 2 into 10 to the power 12 centimeter minus 3, and 10 to the power 14 centimeter minus 3, 2 into 10 to the power 12 centimeter minus 3, and 2 into 10 to the power 6 centimeter minus 3. Option A is 0, and 10 to the power 20 centimeter minus 3. Okay. So these are the options. See, the question says, consider energy level diagram shown below, which corresponds to the molecular nitrogen laser. Hmm. So this is the transition 2 to 1, tau to 1, tau 1, and this is R. Pump rate R is given 10 to the power 20 atoms per centimeter per second, that is. Decay rates are given, tau to 1 is given as 20 nanoseconds, and tau 1 is given as, how much is this given? 1 microsecond. Okay, so what are you asked? The equilibrium populations of states 2 and 1 are. That means you have to calculate equilibrium population N2 and N1. Okay, so how to write this equation? Can you tell me? Can you see? D. How will I write the equations? dN2 by dt. See, to state 2, R is going into it, so R will be positive. The one that is going into is positive. What is going out? Tau to 1 is going out, so minus N2 by tau to 1. Okay, yeah, tau to 1 is going away from 2, so that will be negative. R is going into, that is positive. Now, can you tell me dN1 by dt? See, dN1 by dt here, tau to 1 is coming towards it, right? Tau to 1 is coming towards it, that will be positive. So N2 by tau to 1, that's positive. It's coming towards it. Tau 1 is going away from 1. Okay, tau 1 is going away. The one that is going away is negative. So N1 by tau 1. Is that clear? Huh? Yeah, yeah. So I will write it here. See, again, I will explain. This is R going into, this is 210. So R, this is tau to 1, this is tau 1. So R is going into 2, so R is positive. If I write the equation for rate equation for state 2, R is going into, so R is positive. Tau to 1 is going away, so minus N2 by tau to 1 will write, not tau to 1. This should have same dimension. Okay. Now what? dN1 by dt will be what? See, this is one state. From one state, tau to 1 is coming towards the state, so tau to 1 will be positive, and tau 1 is going away, so tau 1 will be negative, and their corresponding n values. So, what is asked in the question? The equilibrium
populations of state to one state. So at equilibrium, what happens? At equilibrium condition, or at equilibrium, this dn1 by dt. Just a second. Just a second. Hello, hello. Good morning, ma'am. Oh, ma'am. Again, ma'am. Again, ma'am. First year ना second year. Again. ठीक है चलो 4:30. आगे मैम आगे मैम 4:30 तो आगे ठीक है चलो थैंक यू I'm sorry for that. Okay. At equilibrium, dn1 by dt is equal to dn2 by dt in equilibrium condition. Okay. So, dn by dt is this one n2 by tau t1 minus n1 by tau 1 is equal to dn2 by dt, that is r minus n2 by tau 2. Is that all right? Yeah. Hmm. Yeah. So, if you see, uh, okay. So if I write the equation 2n2 by tau to 1 is equal to r plus n1 by tau 1, right? R plus n1 by tau 1. So n2 will be what? Tau to 1 by 2 r plus n1 by tau 1. Hmm. Okay, I did a mistake. Wait. Okay, so here, see at equilibrium, this is equal to 0. Okay, forgot about that. Sorry. So this equal to this is 0. So r minus n2 by tau to 1 is equal to 0. So r is equal to n2 by tau to 1. So n2 is equal to r tau to 1. Alright. So your r is given as 10 to the power 20. Tau to 1 is given, that is 20 nanoseconds, that is 20 into 10 to the minus 9. So 20 into 10 to the power 11. Okay, 20 into 10 to the power 11. What? The unit should be centimeter minus 2. Okay, that is 2 into 10 to the power 12 centimeter minus 3. Yeah. Now n1. Now n2 by tau to 1 is equal to n1 by tau 1. So n1 will be what? Tau 1 by tau 2 1 into n2. We just got n2, right? So tau 1 is your 1 microsecond, that is 10 to the minus 6. Tau 2 1 is 20 nanosecond, that is 2 into 10 to the sorry, 10. Yeah, 20 to the power 10. No. 2 into 2 into 10 to the power minus 8. No. Into n2 we got as 2 into 10 to the power 12. So 2 cancels out. This goes 10 to the power 2. So this becomes 10 to the power 14. So n2 is your n1 is 10 to the power 14 and n2 is 2 into 10 to the power 12 centimeter minus 3. Yeah, that is the answer. If you check the options, yeah, that's one of the answer. Option A. Oh, population of 2 and 1. Sorry. 2 and 1. 2 is your the 14, 1 is your. Yeah, don't do this mistake, okay? Despite doing it perfectly, you will lose marks. Okay. So this was your what? Question number. This was your question number 20.
Just a second, let me find a good question. Anyway, right from the same chapter, 20, question number 20. Consider a hydrogen atom. Consider a hydrogen atom undergoing a 2p to 1s transition. Undergoing a 2p to 1s transition. Okay, the lifetime TSP of the 2p state for spontaneous emission the spontaneous emission is 1.6 nanoseconds, and the energy difference the energy difference the energy difference between the levels is 10.2 electron volt. Okay, assuming that the ri of assuming that the ri of the medium assuming that the ri of the medium um, in ri means refractive index of the medium n naught is 1. the ratio of the ratio of Einstein coefficients the ratio of Einstein coefficients for stimulated and spontaneous emission stimulated and spontaneous emission B21 omega by A21 omega is dash. Okay, this is the question. See, read the question again. Consider a hydrogen atom undergoing a 2p to 1s transition. The lifetime TSP of the 2p state for spontaneous emission is 1.6 nanosecond. The energy difference between the levels is 10.2 electron volt, assuming that the Ri of the medium is this much. Ratio of Einstein coefficients. Okay, so the Einstein coefficients B21 omega by A21 omega, it has a formula for it. The formula is pi square CQ divided by h squared omega q n not q. All right, this is the formula for your this one Einstein coefficient relation. You have to remember this. There's no other way. And if you put all the values, you will get the simple answer. But the thing is, you have to remember this. And n naught is given as 1, and del E is given 10.2. So okay. So del E also given. So we don't have del E here. So what can we do here? We have to expand this formula, and that will be, remember this formula also, del E Q and not Q. Yeah. This is the final formula. Just remember this one at least. What is this? h naught square pi square CQ by del E Q and not Q. Okay. Yeah. So we did 10 questions in this class. I hope you understood. If you didn't understand at any point, please let me know in the comments. All right. Yeah. Okay. Okay. Thank you very much for watching.